In a control system, it's often wise to increase the gain KR of the controller because it makes the system faster, it reduces static error, and it reduces the impact of disturbances. However, a larger proportional gain may have impact on the stability of the closed-loop system. In this video, we're going to discuss the impact of increasing the proportional controller gain on the stability by looking to the so-called root locus. And the definition of the root locus is the mapping of the poles of a control system as a function of the loop gain. Let's look to this situation in which we have a system over here, H, and we have a system over here, G. This system H is in the forward branch and this system G is in the feedback loop. So we can define an output signal C over here, which is the control value, and we can define a set point, a requested value over here, R. And by having this system, we can define the transfer function between the output of that control system C over the input signal R. We can say C over R are all the systems in the forward branch divided by 1 plus all the systems in the loop. So we get kr times h in the numerator divided by 1 plus kr times h times g in the denominator. So this is my transfer function for that feedback system. Kr times h times g is also called the open loop transfer function. Now we can define the poles of this system by setting the denominator to 0, so we get 1 plus kr times h times g is 0. Or in another way, we can say, well, this 1 can be put to the right side of the equation with a minus, and then we get h times g is minus 1 over kr, and that is what we call the root locus equation, the RLE. So it's nothing more than the denominator of the transfer function of the closed loop system setting to 0. So it's the definition of how we can calculate the poles of my closed loop system. And we mostly put it in this form. So all the blocks in my closed loop system, except for kr, are equal to minus 1 over kr, the root locus equation. Let's start with an example. And in this example, we have a system block HP over here, and we have no system anymore in the feedback loop. So HP is 2 over 50s plus 1. So HP is a first order system. Now we can define C over R, and C over R are the blocks in the forward branch, KR times HP, so KR times 2 over 50s plus 1, which is the numerator over here, divided by 1 plus all the blocks in the complete feedback loop. So 1 plus kr times HP, so 1 plus kr times 2 over 50s plus 1, which is in the denominator over here. So now we can get rid of the fractions by multiplying the numerator and denominator by 50s plus 1, and then we get 2 times kr divided by 50s plus 1 multiplied by 1, which brings 50s plus 1 plus 2 times kr. Now we can calculate the pole of this closed loop system. And the pole of this closed loop system can be calculated by setting the denominator to 0. So by setting 50s plus 1 plus 2 times kr to 0. So then we get 50s is minus, and then between brackets 1 plus 2 times kr, so s is 1 plus 2 times kr divided by 50 with a minus in front of it. That's the location of the pole. And what we see is that that location of the pole is depending on the value of the proportional gain kr. Proportional gain kr is the setting of my controller. So when we set kr to 0, we see that the location of the pole is minus 1 plus 0 divided by 50. So the location of the pole is then minus 1 over 50, which is exactly the location of the open loop system over here, which is also minus 1 over 50. When we increase the gain, we see that the pole starts to move. So for instance, when kr is 2, then the pole location is minus 1 plus 2 times 2, which is minus 5 over 50, which is minus 0.1. And we can do that for more values of kr, and we can put them in an S-plane, and then we see the so-called root locus, which indicates that the pole starts over here when kr is 0. When kr is 2, the pole is at this location minus 0.1. When kr is 5, the pole location is minus 0.22, etc. So the pole moves from this point to the left, and that is what we call the root locus. We put an arrow over here which indicates that in an increasing kr the pole moves in this situation to the left. That is the root locus. That was the first order system with which we started to look to the root locus. Now let's look to another system, for instance a lead lag filter. And a lead lag system has at least one 0 and one pole, and in this situation HP is S plus A divided by S plus B. So that's the system HP over here. And again we can calculate the feedback, the transfer function between the output of the control system C divided by the input R. And we do it in the same way as we did it before with the first order system. We say C over R is kr times HP divided by 1 plus kr times HP. Again, all the blocks in the forward branch divided by 1 plus all the blocks in the loop. So kr times HP divided by 1 plus kr times HP. The poles of this system can be calculated again by setting the denominator to 0. So 1 plus kr times HP is 0. And that is what we call the root locus equation again. So it's equation for the poles of my closed loop system. Well, put it in another way, we fill in the transfer function for HP, we get 1 plus kr times S plus A divided by S plus B is 0. And we can get rid of this fraction by multiplying all the parts in this equation by S plus B. So then we get S plus B over here. This part of the equation will be kr times S plus A, and this stays 0 because 0 times S plus B is 0. So now we have this as my equation, and we can put all the parts with the S together and all the constant parts, and then we get 1 times S, which is this part, plus kr times S, which is this part, plus the constants B plus kr times A is again 0. So the location of my pole is, by putting this to the right side of the equation, so it becomes a minus in front of it, and then dividing it by 1 plus kr, it yields S is minus B plus kr times A divided by 1 plus kr. So again, we see also for this system that the pole location is depending on the value of kr. So let's look at first when kr is 0. When kr is 0, this will become 0 and this will become 0, so S is minus B divided by 1 is minus B. So my root locus starts at a value of kr is 0 and S is minus B. And notice that S is minus B is also the pole of my open loop system, so the pole of HP. When kr is infinity, so it's the largest value possible, then in the numerator we can neglect the b with respect to this infinite number. And in the denominator we can neglect the 1 with respect to this infinite number. So then we get a times kr divided by kr is a. So the pole for kr is infinity is in S is minus A. And from this equation, my open loop system, HP, we see that S is minus A is the location of the 0 of my open loop system. So at kr is infinite, is an infinite value, so infinity, the position of the pole of my closed loop system is the 0 of my open loop system. So it's in S is minus A. So now we can draw the root locus. For a case where A is smaller than B, the position of the pole is over here and the position of the 0 is over here. So we see that for kr is 0, the root locus starts over here and the pole of my open loop system, and for kr is infinity, it ends in the 0 of my open loop system, and that is in minus a over here. So we draw the root locus like this, and we can put an arrow in it which indicates the value of the root of the closed loop system when kr increases. So the root locus is like this. It starts over here and it ends over here. When B and A are swapped, then again the root locus starts in the pole and it ends in the 0, and this is the root locus, how the pole moves when kr is increasing. So now we have seen that we can define the root locus for two simple systems, but you can do it for more complex situations. And for every situation in which you want to construct a root locus, there are a lot of root locus construction and calculating rules. We are not going to discuss them in detail because we are mostly defining and drawing a root locus by using MATLAB. But for simple systems, we must be able to do it by hand. And for these simple systems, the rules number 3, 4, 5, 7, and 8 are applicable. So look into these rules, and we are seeing how we can apply these rules to simple systems. So these rules are neglected. These are implemented in MATLAB. So let's look to a simple system like HP is s minus 2 divided by s plus 2 times s plus 4, the system over here. We are going to construct the root locus for this system again by using the rules which we defined over here. We're going to use these 5 rules which I indicated in blue. So this system has 1, 0 and 2 poles. 1, 0 because there is only one s in the numerator, and the numerator and the location of that 0 is in s is 2. And we have 2 poles, and these poles are located at the location points s is minus 2 and s is minus 4. Well, now we can define the root locus equation by saying that all the system blocks in the loop except for kr are equal to minus 1 over kr. So that is depicted over here. S minus 2 divided by s plus 2 times s plus 4 equals minus 1 over kr. And of course, you can also calculate this root locus equation from the denominator of the closed loop equation, C over R. So we have in this situation, we have our root locus equation, and from that root locus equation, we can draw the root locus. So we start off with rule number 3. We have 2 poles, so we see that the root locus will consist of 2 branches. And these poles are, as we have seen, in minus 2 and minus 4. So when we draw the S-plane over here with the real axis on the horizontal axis and the imaginary axis on the y-axis, we see that the pole locations are in minus 2 and minus 4. Rule number 5 says that we have 1, 0, and because of the fact that we have only 1, 0, one branch of the root locus will end in that 0, so the 0 at this point, s is 2, and the other branch will end in infinity. Rule number 7 says that the root locus is symmetric with respect to the real axis. And rule number 8 is an important one. It defines which part of the real axis are belonging to the root locus. Well, it says that when we travel on the real axis from right to left, we add all the poles and zeros which we see on these points of the real axis. And when the total number of zero and poles are odd, then the part of the real axis belongs to the root locus. So let's do it. We start off over here at the real axis, and over here we see a 0. So the total number of 0 and poles at this point is 1, and 1 is an odd number, so this part of the real axis belongs to the root locus. At this point we see a pole, so the total number of poles and zeros is at this point 2, which is not odd, so this part of the real axis does not belong to the root locus. At this point we see a pole again, so the total number of poles and zeros is 3, so again it's an odd number. So this part of the real axis belongs to the root locus. So it is indicated by these red lines. Well, now we can construct the complete root locus. We had these parts, and we see that the root locus start off in the poles and it ends in a 0 or in infinity. So these are the root locus branches. And again, the arrow indicates how the poles move when Kr increases. All right. Um, we did that by hand, but we can check our result by using MATLAB. And in MATLAB, we can define a transfer function with a numerator s is minus 2 and a denominator s plus 2 times s plus 4. And we do that in MATLAB by defining the coefficients of the numerator. The minus 2 is the constant value over here, and the 1 is the 1 times s over here. The denominator coefficients can be defined as follows. We work out this equation. It is equal to s squared plus 2 times plus 4 times s. So it's 6 times s plus 2 times 4 is 8. So we have the coefficients 8, the constant value, 6, the value in front of the s, and the 1 in front of the s squared. Now we can use the MATLAB command tf, which is the transfer function. So we can define HL, so the loop transfer function, which is equal to the transfer function of the numerator and the denominator. And when we have defined that, we can use the MATLAB command root-locus, r-locus, to draw the root locus. And when we add this in MATLAB, then we get this as the root locus plot. And it's exactly the same plot as we calculated by hand. We have the pole locations over here, and we have the 0 over here, and we see that these are the root locus branches. Now we can also calculate for which value of Kr the closed loop system will become unstable, because what we see is that one pole moves to the left, so it moves in the left half plane, so this pole will never lead to instability, but this pole will cross the imaginary axis over here. So from this point on, this pole moves into the right half plane, and we have seen that at least one of the poles is in the right half plane, then the complete system will be unstable. So this point, which is the origin, is the point at which my system becomes unstable. So what will be interesting is that we can calculate the value of Kr at which the complete system will become unstable. So what we are doing is we are going to define the root locus equation again, and we fill in that value of s for which the system will become unstable, which is in this case s is 0. So okay, this is my root locus equation. S minus 2 divided by s plus 2 times s plus 4 equals minus 1 over Kr. And for s is 0, the corresponding Kr indicates the value of Kr at which the system will become unstable. So let's fill in s is 0 over here, and then we get 0 minus 2 divided by 0 plus 2 times 0 plus 4 is equal to minus 1 over Kr. So we can calculate that the corresponding Kr will be equal to 4. 2 times 4 divided by minus 2 with a minus in front of it. So we know that at Kr is 4, instability starts to occur. So when you have this system, never increase Kr to values higher than 4, because at that value of Kr, your system will become unstable. We can also indicate that point by MATLAB by putting a cursor over here, and then you see that MATLAB also calculates the corresponding gain. Note that the resolution is not exactly the right spot in which instability occurs, because the pole is not exactly in the origin, but it indicates that at a gain of 4, my system becomes unstable. Also note that when you have another transfer function, the root locus can rather have a different shape with respect to the original shape of the shapes of the root loci which we discussed. Suppose that the minus 2 over here is replaced by a plus 6 over here. Then this is my transfer function, and this is my root locus equation. S plus 6 divided by s plus 2 times s plus 4 is equal to minus 1 over kr. This is typically a transfer function for which we are going to use MATLAB to see what kind of root locus this system will bring us, so to say. We see that the pole locations are here at minus 2 at and at minus 4, and that the location of the 0 is not at s is 2 anymore, but at s is minus 6. And then the root locus, when we construct that by using MATLAB, looks like this. The two branches start from the pole, so one moves to the right side and one moves to the left side, and somewhere between 2 and 4 they split off and they form a so-called circle. This is a circle, and this is a circle because the values on both axes are not the same. This is from 3 to minus 3, and this from minus 10 to 1, so this is really a circle. And between minus 8 and minus 9, these two branches intersect with the real axis again, and then one pole moves to the 0 at minus 6, and the other pole moves to minus infinity. So in this situation, we have seen that by having the 0 on a complete different place, we get a complete different root locus. But summarized, we can see that by looking to the root locus, we see how the poles of the closed loop system change, and we can determine the impact on stability. That's all about the root locus. Thank you for watching, and I see you next time.